Okay, I'll get started. Today's class, we're continuing our work on light, which was built on our work on electricity and our work on magnetism. In today's class, I want to talk about a device, an instrument that is the Michelson interferometer. It's built on our understanding of reflection and refraction and diffraction, all the ingredients we've been talking about over the last handful of classes. And we're going to explore this device, how this device works, the use of this device for various experiments, and in particular the use of this device to get a deeper understanding of light and what light was, what light's vibration was. So specifically, I want to walk through these three bullets. We'll talk about the Michelson interferometer and the interference of light. We'll look at the Michelson interferometer's application to measurements of wavelengths of light. It can very precisely measure wavelengths of light. We'll talk about the Michelson interferometer's application to measurements, very precise measurements of short distances, like sizes of cells or bacteria. And then finally we'll talk about the interferometer's application to detecting something that in the 1800s was called the ether. The ether was a hypothetical material in the 1800s. It was the hypothetical material in which light existed, in which light was a vibration. So it was deeply connected, the ether, to our understanding of light, our understanding of the nature of light. So we'll walk through these bullets. This should be indices. I don't know how that happened. And this doesn't work. So, Michelson interferometer. How does Michelson interferometer work? What is the Michelson interferometer? It's based on, as I had mentioned, it's based on interference and our understanding of interference. It's due to Albert Michelson, who invented it. He got the Nobel Prize in early 1900s for the use of it. What's interesting is that he got Nobel Prize for an experiment that used the Michelson interferometer, but the experiment failed in what it was planning to do. But it was such an important failure of an experiment, it's sort of the classic failed experiment, that it caused a deepening of our understanding of nature, and in particular our understanding of space and time. So it was a failed experiment, but it opened up our failed understanding, a misunderstanding of something very important, and that was space and time. Okay. So just as a reminder, I've got two slides because these are crucial ingredients in understanding the interferometer. The two slides I showed in a previous class, maybe a couple of classes, 2 or 3 classes ago, on interference, when I introduced interference. And basic idea is that interference occurs when you have two overlapping, superimposing, coalescing waves. And there's two extremes of interference. There's constructive interference where the waves overlap with one another and they're what we call in phase. The phase between the two waves is 0 degrees. That means that crest and crest combine together to make a larger crest. Trough and trough combine together to make a deeper trough. So that's constructive interference. That's going to go on in Michelson experiment. Interferometer. The other slide that doesn't work, got from a previous class, was the other extreme, which is destructive interference. So destructive interference occurs again when you've got two waves that superimpose with one another, coalesce, combine with one another. In this case, the two waves are what we call out of phase, which means that there are 180 degrees phase difference in the two waves, which means that when one is a crest, the other is trough. When one is trough, the other is a crest. And so when they combine together, they cancel each other out. This is this amazing effect of two waves adding together to, in total, create complete darkness. Nothing. And so that's destructive interference. And the Michelson interferometer involves destructive interference as well. So this is just a few bullets to describe how the Michelson interferometer uses constructive, destructive interference, how it works. And then we'll go on and look at a Michelson interferometer and see in more detail how it works and some equations for how it works. But basically what it does, if we walk through these 4 bullets here and what it is used for, it takes a beam of light and it splits that beam of light into two separate beams of light. So it divides a beam of light into two halves. Those two beams of light are then recombined, and when they recombined, they interfere with one another, and you can get constructive and destructive interference. And this might remind you of the class a week ago where we discussed two-slit experiment, which is where we split a beam of light into two beams with the two slits, and then we let them interfere. Or it might remind you again a week ago of the soap bubble interference, where we also sort of split light into two beams, one that came from the top outer surface of the soap bubble, one from the bottom inner surface of the soap bubble, and those two sources of light interfered with one another. And so the Michelson interferometer is just another way of creating, by splitting a beam of two and creating the interference of the two beams, having two sources of light interfering with one another, producing constructive and destructive interference. The way it's done in the interferometer is such that you can use the interferometer for very, very, very precise measurements of light's wavelengths. You can measure very, very precisely the thickness of materials or the length of materials, for example, a bacterium or a cell. You can also measure very, very precisely. Remember there was that property of optical materials, refractive index. You can measure the refractive index of materials very, very precisely. So things like the measurement of the wavelength of a light ray, the length of a cell, the refractive index of a material, they're almost precisely measured with a Michelson interferometer. It's the technique for most precisely measuring those things. As I say, it has, and we'll see this towards the end of the class, that it also, in addition to being a very precise, accurate instrument that's useful, it led to a discovery, an unexpected discovery about nature of space and time. So here is a view of Michelson interferometer. This is a helicopter view of a Michelson interferometer. And then over here on the left-hand side, I'm just going to explain some details about how it exactly works. So here we are looking down on the interferometer. In the interferometer is a source of light. It's over here on the left-hand side. There's also a screen in the interferometer to see the interference pattern that's created by the source of light. So there's those two ingredients. And then there's arrangements of mirrors, various mirrors. And so that's all these mirrors over here that I want to explain. Let's follow the light ray as it travels from the light source on the left into the interferometer here in the center. The first thing it does is strike a partially silvered mirror. So what's a partially silvered mirror? A partially silvered mirror is a mirror that reflects some light because it's only partially silvered, and then transmits the remaining light. The remaining light is not reflected, it is transmitted. So a fully silvered mirror would reflect all light, like in your bathroom. But a partially silvered mirror will actually reflect a fraction of the light, say half the light, and transmit half the light. And so this is where the splitting of the light into two happens, at this center mirror. Some of the light is reflected, and when it's reflected, it heads upwards, upstairs here. Some of the light that's transmitted carries on basically in the same direction, and it continues heading to the right here. So that's the first part of the interferometer, that splitting of the light into a beam that's going to go up towards the ceiling here, and another beam that's going to go over towards the right-hand side. On the ceiling, the top of the interferometer in the sketch, is a mirror. This is a fully silvered mirror that's going to reflect all the light. On the wall over here, or on the right in the overhead, there's also a mirror. It's a fully silvered mirror. Again, it's going to reflect all the light. So light is reflected back off this top mirror here. So the light rays that went upwards will come back downwards. The light that went over towards the right here going to be reflected off the right-hand mirror. The light rays that went right are going to come back towards the left. So they come back towards this, again towards this partially silvered mirror. And this partially silvered mirror doing what a partially silvered mirror does, which is reflect some of the light and transmit some of the light, will reflect some of the light that's come from the right, this purple beam here, down towards the screen, and the observer will transmit some of the light that went upstairs here back down towards the screen and the observer. And so we get two beams of light here. You see these two closely separated lines here. One that has originated from the path that went upstairs and then downstairs. The other one is originated from the path that went towards the right and towards the left. And it's these two beams that interfere with one another. Just like, the light from the top and bottom surface of the soap bubble interfered, the light from the two slits of the two-slit experiment interfered, the light that went upstairs and downstairs, and then the light that went left and right, those interfere with one another. You're going to get an interference pattern. You're going to get a pattern of bright and dark fringes that correspond to constructive-destructive interference, and that's what we see here. The important, and maybe the key thing about the interferometer and this observation of constructive-destructive interference through dark, bright fringe patterns, which is not new to us, we've looked at this before, is the fact that this mirror upstairs here is adjustable. This one over here is probably fixed, but this one is adjustable. You can move it. You can move it in this sketch downwards towards the partially silvered mirror, or you can move it upwards away from it. And when you move it downwards or upwards, you change the interference pattern. You change the interference pattern for the light rays because you're changing the path that the light is taken to get upstairs and then downstairs. If you move that mirror further away, the light's got to travel further. It's got to travel further up to the mirror, and it's got to travel further when it goes back towards the partially silvered mirror. So it travels an extra distance, and that means that the light wave will have a different phase. It might be a crest when it was a trough, or it might be a trough when it was a crest. And so we've changed the interference pattern. And so this is basically the experiment here. I think that's probably all I want to say about that. There's one little extra ingredient here. It's really a detail. This glass plate here. The light ray that went up and down, it traveled through this glass of this partially silvered mirror 2 extra times. So typically another plate of glass is added in this left-right path. So to counteract that, this light ray also travels through this plate of glass 2 times. So this enumerates how you use the interferometer. So you can use the interferometer, as I mentioned, to measure wavelengths of light. So shine some light and you're going to measure the wavelength of that light. You're interested in determining the wavelength of that light. Or you might want to measure distances. You might want to measure the distance from one end to the other end of an amoeba. And so you would be using this device to measure distances. So how does that work? Suppose we take this mirror and we move that mirror by 1/4 of one wavelength of the light that's in the interferometer. So we're going to move this mirror by 1/4 of a wavelength. Supposing we move it further away by 1/4 of a wavelength. That means that the light that's striking that mirror now has to travel an extra distance. It has to travel an extra distance 1/4 of a wavelength up to strike the mirror, but it's also got to travel an extra distance of 1/4 of a wavelength down to return to the partially silvered mirror. So if we move the mirror by 1/4 of a wavelength, the light is traveling an extra 1/2 a wavelength. If that light ray that went up and then down is traveling an extra 1/2 a wavelength, but we haven't changed the path that's traveled by the light ray that went left and right, then what are we going to do? We've changed a crest of the up-down light ray to a trough, because we've added an extra 1/2 wavelength path difference. We've changed a trough of the up-down light wave to a crest because we added this extra 1/2 a wavelength path distance. And so this fringe pattern is going to change. What we're going to see is that a dark fringe, what was a dark fringe, once we move the mirror by 1/4 of a wavelength, becomes a bright fringe. What was a bright fringe, when we move the mirror by 1/4 of a wavelength, now becomes a dark fringe. And this is called a fringe shift. It's a fringe shift from bright to dark or dark to bright, and you get one fringe shift when you move the mirror by 1/4 of a wavelength. And so this is a key to using the instrument to measure wavelengths and measure distances or lengths, is the relationship that we just figured out between the change in the fringe pattern, going from a bright fringe to a dark fringe or a dark fringe to a bright fringe, and the movement of the mirror. The movement of the mirror was a displacement of 1/4 of a wavelength. You can make a similar argument. Supposing instead of moving the mirror by 1/4 of a wavelength, we move the mirror by 1/2 a wavelength. If you move the mirror by 1/2 a wavelength, then the light that's heading up towards the mirror has to travel an extra distance. It's half a wavelength extra distance. But it also has to travel another 1/2 a wavelength extra distance as that light ray moves downwards back towards the partially silvered mirror. So if you move the mirror 1/2 a wavelength, then the light ray travels in total a change in distance that's 1 whole wavelength. If you've added a whole wavelength extra distance to the up-down path here, but you didn't add it to the left-right path here, then that means that the fringe pattern has changed, but it's gone from, if supposing it was a bright fringe, it's gone from a bright fringe to a dark fringe and then back to a bright fringe. That's what we call one complete cycle, one complete fringe cycle, bright to dark to bright. Or maybe it started out dark, you moved the mirror by 1/2 a wavelength, you added a full wavelength of extra path for the up-down light ray, you've changed that dark fringe to a bright fringe and then back to a dark fringe. So again, that's one complete fringe cycle from bright to bright, or dark to bright to dark. So if you want to measure a wavelength, the way that you measure a wavelength is that you move a mirror a certain distance. you count how many fringes, how many fringe shifts happened. You know, maybe there's 1,000 fringe shifts. Or you count how many fringe cycles happened. Maybe there was 500 fringe cycles. And from that information, the distance that you move the mirror and the number of fringe shifts that you observed, you can calculate the wavelength. So that's how you would calculate a wavelength with an interferometer. Alternately, if you're measuring the length of an amoeba, or the size of a cell, or the size of a bacterium, then you would again move the mirror along the length of the cell or the amoeba. You would move the mirror that unknown distance. You would count the number of fringe changes. So maybe there was 5,000 fringe shifts or 500 complete fringe cycles. You would count those shifts or cycles. If you know the wavelength of the light that you're using, then you can use that information, the number of fringe shifts or fringe cycles, and the movement of the mirror, due to the movement of the mirror along the cell, you can calculate the length of the cell, knowing the wavelength of the light. So that's how you measure a very small distance. You have to know the wavelength of the light and count the fringe shifts or fringe cycles, or you measure the wavelength of the light. You have to know how much you move the mirror, and then with that information in how many fringe cycles or fringe shifts, you can calculate the wavelength of the light. I keep trying to use that, but here's a real interferometer. This is kind of what it looks like. It doesn't show the light source in this picture. So there's a light source downstairs here on the bottom left, and it doesn't show the screen on this picture. There must be a screen and an observer over here on the bottom right. But here comes the light heading in from the bottom left. This angled mirror here is that real important mirror, is the partially silvered mirror. This is the one that's going to split the light into two. It's also the one that's going to recombine the light into one. So it is dual purpose, splitting the light rays and then recombining the light rays. So when the light first strikes the mirror, some is reflected over towards the right here, hitting mirror number one. Some is transmitted over towards the top right here, hits mirror number two. And then those light rays bounce back in both cases on the left and right, because those are fully silvered mirrors. They strike the partially silvered mirror again in the center here, and that combines some fraction of these returning light rays into this outgoing light beam that exhibits the interference, constructive destructive interference, exhibits the fringe patterns, the bright and dark fringes. And then upstairs here is the adjustable mirror. This is the one you can move in and move out. If you want to measure the wavelength of the light that you're shining into the interferometer, you move that mirror a known distance, count the cycles. If you want to measure the length of an amoeba, you move the mirror along the body of the amoeba, and knowing the wavelength of light and counting the fringe cycles, you can calculate the length of the amoeba. I've sort of mentioned it, but let me summarize it here. One shift, one dark bright shift, or one bright dark shift, that corresponds to moving the mirror 1/4 of a wavelength. So this quarter of a wavelength corresponds to a dark bright shift or a bright dark shift. If you count n, a number of bright dark shifts or dark bright shifts, the movement of the mirror then is n times that lambda over 4. So this is a useful equation. It relates the distance you move the mirror to the number of fringe shifts, that's the uppercase N, and the wavelength of light. That's how those three things are connected. They're all distances, right? Length of the wavelength of the light, lambda, the distance that you move the mirror, and then a number, which is the number of fringe shifts. So that's how the three things are connected. And if you know any two of them, you can calculate the third. So that's if we know the movement of the mirror, d, and we know the number of fringe shifts, we can calculate the wavelength. Or if we know the wavelength and we know the number of fringe shifts, we can calculate the distance d. So this is for what I called fringe shifts from dark to bright or bright to dark. This is the same sort of equation, but for complete cycles. We called a cycle where you went bright, bright, or dark, bright, dark. In that case, the mirror's moved by lambda over 2. In that case, the distance that you've moved the mirror, the wavelength of the light, and the number of cycles now, so this is the number of cycles, this was the number of shifts, is related by this little equation here. It's d equals n lambda over 2. So again, if you know the distance you move the mirror, you can calculate the wavelength by calculating the number of fringe cycles. If you know the distance that you move if you know the wavelength of the light, you can calculate the distance you move the mirror, again, by calculating by counting the number of complete fringe cycles. So this is an important equation too. And you just use the top one or the bottom one, whether you counted just shifts from dark to bright, or vice versa, or you counted cycles, where you went, dark, bright, dark, or bright, dark, bright. And that's just personal preference, right? There's nothing special about one or the other. Okay. Oh, I was going to show a video. So this is a video that shows you the use of an interferometer. I believe it's for measuring the wavelength of light. And it'll just walk us through, again, the components of the interferometer, and then a demonstration of measuring fringe shifts or fringe cycles and determining the wavelength of light. So in this case, there's a laser, a helium laser. It's over there on the left. That is the source of the light. It has a known, I think we're going to measure the wavelength of that. Here's this, the splitter. We've just seen these two mirrors. One's movable. This is how you move the mirror. And now we're going to use that arrangement to measure the wavelength of the helium laser light. Here is whoever this is, I don't know, is moving this mirror over here, and you see the fringe pattern changing over here. You see this beautiful pattern of it going from bright in the center to dark in the center, and so on and so forth. You see these fringes. You're walking through these fringes as you're moving the mirror to and fro. So whoever's demonstrating this is going to count these fringes. So he's put them on a screen. He's been very careful, and he's marked the position of this particular dark fringe. So this is going to be his reference point. And then he's going to move the mirror a known distance. So he started at 0, and look, he's moved it a certain distance, and we moved 1 complete fringe, 4 complete fringes, 5, so on and so forth. He's counting how many fringe cycles there are when he's going to move the mirror a known distance on his little micrometer. And I think he moves it, let's see, quite a few times. 20 times. He completed 20 cycles, complete cycles, and he's moved the mirror 6.5 micrometers. So using that information, using the number of fringe cycles, that's the uppercase N, using the distance that you move the mirror, then he could calculate the wavelength of the light. And that's how we use the interferometer. Okay, stop that. Let me just work through an example. So in this particular example, we're told that the mirror was displaced, this is 0.38 millimeters, so it's 382 micrometers. So it's a fraction of a millimeter, 0.38 millimeters. And when we did that, we were even more careful, and we counted 3,400 bright to dark fringe shifts. So it's total number of fringe shifts from bright to dark or dark to bright. So we've moved the mirror a known distance. This is the D. We counted a known number of fringe shifts. This is the N, and we're just going to determine the wavelength of light based on that. And we're going to determine the wavelength of light with this idea that you get one fringe shift if you move the mirror by a quarter of a wavelength. You get one complete cycle if you move the mirror by half a wavelength. So let me just calculate that on the document camera. Here we are. So I wrote out the information we were given in the problem. The distance D that we moved the mirror, 382 microns. The number of shifts, this is from dark to bright or bright to dark, was 3,400. With this information, we can calculate the wavelength. The master equation was this one here. You get one fringe shift when you move the mirror by a quarter of a wavelength. If you get n fringe shifts from a distance of moving the mirror d, then this is the relationship between the wavelength and the distance you move the mirror and the number of fringe shifts. Now, we want to solve this for the wavelength, so I've just got to rearrange it. I've got to multiply by 4 and divide by n. So I get this little equation here, and I can fill in that I got 4 times, this is 382 micrometers, so stick that in. And divided by n, that was 3,400. And if I calculate that, I got 0.449 micrometers. That's 449 nanometers. And so that's the wavelength of the light. 449 nanometers is a short but visible wavelength of light, is blue wavelength light. And so we've solved for the wavelength of light by moving the mirror a known distance and counting the fringe patterns. We could have done the same calculation using fringe cycles. That's why I wrote this down here. So the relationship between the distance and the number of fringe cycles and the wavelength of the light was this one here. A change of one fringe cycle moves means the mirror has moved by a distance of half a wavelength. So we could have used this, except in this case the number of cycles would be 1/2 the number of shifts, because a cycle is two shifts. So if you plug all the numbers in for this equation, if I was to redo the calculation but using cycles rather than shifts, the number of cycles would be half as big, but this number in the numerator is half as big. It's 2, not 4, and so you would get the same answer, 0.449 micrometers, or 449 nanometers, which is the blue light. Okay. I put in here, I won't do this second example, but I put in here a second example. We just did the example of measuring the wavelength of light using the interferometer by moving the interferometer mirror a known distance and counting the fringes. You can measure a distance, an unknown distance, knowing the wavelength of light and again counting the fringes. So there's an example of that in here, but it's the same sort of problem. Let me just do this quiz question and then we'll move on. I didn't publish it, sorry. So in this problem, we're not using the interferometer to measure the wavelength of light. We're using the interferometer to measure an unknown distance, the length of bacteria. And the question is, if you decrease the wavelength of light, so if instead of using long wavelength light, an example of that would be red light, we decrease the wavelength of light, an example of that would be blue light. So if we went from 700 nanometers, that's red light, to 400 nanometers, that's blue light, would we get more fringes, more fringe changes as we move the mirror along the bacterium? Would we get less fringe shifts as we move the mirror along the from the top to the bottom of the bacterium, or will we get the same number of fringe shifts? So I'll give you a moment to think about that. So in all these examples with the interferometer, we're using a master equation, or two versions of a master equation, where we relate three quantities. The three quantities are the wavelength of light, that's a distance, a length, are the movement of the mirror, that's the distance we move the mirror, and the number of either fringe shifts, dark to bright, bright to dark, or complete fringe cycles, bright, dark, bright. So we're relating those three quantities here. And this is the equation, the version of the equation where this is the number of fringe shifts. And so this is a relationship between the distance the mirror moved, the wavelength of the light, and the number of fringe shifts. If I was to move along the length of the bacteria with long wavelength light or with short wavelength light, I'm moving along the length of the bacteria in both cases, whether I'm using the red or the blue light. So the distance is the same. D is the same in this this quiz question. I'm always moving the same distance. D is the length of the bacteria. What I'm changing is lambda. I'm going from long wavelength to short wavelength. If D is the same and I decrease the wavelength, I have to increase the number n, the number of fringe shifts, or the number of fringe cycles, for this equation still to hold. So if you use shorter wavelength light, like blue light, instead of longer wavelength red light, you'll get more fringe shifts based on this equation for a given movement of the mirror. That can be very useful, right? Your accuracy is determined, affected by counting the fringe shifts, counting the fringe cycles. If you use shorter wavelength light, you'll make more fringe shifts, more fringe cycles. So your counting will, in that sense, be more accurate. So it may be useful to use blue light instead of red light to get a more accurate length of the bacterium. wanted to show you the most famous, presumably now, the most famous Michelson interferometer. So this was an interferometer that is built over decades, and was the interferometer that was in the news a decade ago now, but it was in the news for the discovery of gravity waves. So gravity waves are waves literally in the fabric of space and time. They're kind of ripples in the fabric of space and time. And they're created in the universe or the cosmos, you know, by explosion of stars or collisions of stars, which create these ripples in space and time that propagate outwards like other types of waves, like water waves or sound waves or light waves, but they're literally gravity waves in space and time that are predicted by Einstein's theory of space, time, and gravity. So this interferometer measured those waves. It's huge by comparison to the interferometer that we saw in the video, or that we saw in the photograph. So the arms in this interferometer are about a mile long. Here's one arm, here's another arm. This is the partially silvered mirror downstairs here. This is the location where the beam of light is split in two and then recombined into one. So that's in this building here. Upstairs here is one mirror that reflects light that heads, some of the partially reflected light, say, that heads up to this mirror and is reflected back. Over here on the right is the other mirror, again a mile away, light that was transmitted from the partially silvered mirror, heads up to this mirror and is reflected back, and then the interference is observed. This is super, super precise because the ripples in space and time due to a supernova explosion or a black hole collision are tiny, tiny, tiny effects. This device can measure the movement or change in position, change in location of the mirrors to 10 to the minus 19 meters. So it's an incredibly small distance, and that's the level of the ripples in space and time that are caused by black hole explosion, supernova explosions or black hole collisions, things like that. You get these tiny, 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 tiny ripples in space and time, and this device was able to measure those ripples as they pass through Earth and pass through the interferometer here. And confirmed Einstein's theory of gravity and space and time. So 10 to the minus 19 meters. Think about that. How big, the size of an atom. Atom's small, but atom is, 10 to the minus 10 meters. So atom is small. This is a billionth of the size of an atom. At the very center of an atom is an atomic nucleus. The atomic nucleus is also really, really small. It's 10 to the minus 15 meters, that sort of scale. This is even smaller than that. So it's able to resolve through this interference effect tiny, tiny distances, very, very small distances, and that was needed to detect gravity waves. Okay, now we're going to move on to that last topic I mentioned, which is the using the Michelson interferometer to explore the nature of light, in particular the nature of light's vibrations and the presence of a material called ether. Light was thought to be vibrations in this material called ether in the 1800s. So this was the original theory of light. We talked about light emerging from a unification of electricity and magnetism, a joining together of electricity and magnetism. And when we join together in electricity and magnetism in one unified electromagnetic force, it predicted the existence of a wave, an electromagnetic wave, a wave of electric and magnetic fields, and it predicted the speed of those waves. So I wrote down that equation here. But at the time, just like it was known that sound waves travel in a medium, so most often traveling in air, so we need air for our sound waves to exist and travel and communicate. Just like it was known that water waves exist in a medium, right? They exist in the ocean or a river. They need a medium to exist. It was presumed or assumed that light waves must also, like sound waves, water waves, exist in a medium, and that medium was called ether. It was given the name ether. So, as air was to sound, as the medium that supported sound waves, and water was to ocean, river waves, water was supporting the ocean or the river waves. Ether, this strange material, ether, was what supports light waves. That was the basic idea, the important idea. An interesting thing about ether, though, and a very puzzling thing about ether, had to do with the speed of light waves compared to the speed of, say, water waves or sound waves, and the implications for the nature of ether, the properties of ether. So a very distinguishing thing about light waves is the speed of light waves. So I would say that water waves, they really travel at everyday velocities. So water waves, if you look at ocean waves, they're traveling at meters per second scales. Sound waves, they also travel at kind of everyday velocities. There's a few hundred meters per second, but it's sort of everyday velocities that we can visualize. Light waves, on the other hand, travel at this incredible, unimaginable velocity. 3 times 10 to the 8 meters per second. It's 186,000 miles per hour. That's a huge speed. That's unimaginable for us to picture that speed. So there's a fundamental difference between light waves that sort of travel around almost instantaneously from place to place, and water waves and sound waves that we really notice the time that water waves and sound waves take to propagate from place to place. That has an important implication. The speed of the wave is actually related to the forces that are needed to vibrate the material that the wave exists in. So the speed of a water wave is related to the size of the forces that move the water up and down in the water wave. And the speed of the sound wave is related to the forces that move the air up and down in the sound wave. And the speed of the light wave is related to the forces that are moving the and properties of the ether that vibrate as the light wave moves. Because of the everyday size of water wave speeds and everyday size of sound wave speeds, the forces that vibrate the air or vibrate the water in sound and water waves are everyday scale forces. Because of the very high speed of the sound waves, it's very, very, very large forces that must be involved in vibrating the ether to get the light wave to propagate so fast. So the ether is a very, unlike air, which we can sort of move through easily, unlike water, which we can move through pretty easily, in which the water waves and the sound waves exist. The ether has a property that's extraordinarily rigid and takes enormous forces to vibrate it. So it's much, much, much more rigid than water or air. And it takes much, much greater forces to vibrate it than water and air. And that's peculiar. That's very peculiar because, you know, you and I are moving through the ether all the time, and we don't even notice it. The light is traveling through the ether, so the ether's here, and we're moving through it. Why don't we, if it's so stiff and hard to move, why don't we notice that? The stars and the galaxies and the planets and the sun and the moon, they're all moving through the ether. Why are they just moving round and round in circles or ellipses rather than they're moving through this very, very rigid, almost immovable material? Why aren't they stuck in this material? So it's really puzzling that light suggests that ether must be really stiff and hard to move, but everything else, you and I, and planets and stars, suggests that ether is unnoticeable. It's present, we just move through it completely smoothly. So it's a real puzzle. So at the end of the 1800s, there were experiments to try and detect the ether. This is a big problem, finding the ether, detecting the ether, and there's a lot of effort to detect and find the ether. And the Michelson interferometer was used to try and detect the ether. We're going to see how that works. So I want to show you, I've got a couple of slides related to sound waves. And think about being in the 1800s when we knew what sound waves were and how sound waves work. And then I've got a couple of similar slides about light. Think about being in the 1800s where we weren't certain about light. Was it a vibration in the ether? And these slides suggest a way that we might detect the ether. There's an idea for detecting the ether in here, and it's based on an analogy with what could have been an idea for detecting the presence of air, that the sound waves exist in. Now, of course, we know that air is the material that the sound waves exist in. It wasn't a question, but it was a question what material the light waves exist in. Is it the ether? And so that's why I'm introducing first sound and then air. Look, in air, sound travels at 340 meters per second. That's the speed of sound. And sound literally is a vibration of the air. That's what that sound is. So understanding that sound is a vibration in air is key to understanding the speed of sound waves and the nature of sound waves. An interesting thing about the speed of sound waves, supposing we had a source of sound waves, that's what's pictured here. So here's a loudspeaker in the center. And maybe that's on the desk at the front here. There's a speaker. And it's blasting the sound over towards the right side of the room. And we're all observers in the speaker reference frame, in kind of the air reference frame. We're all in that reference frame. We see the air as still. We see the speaker as still. Now I head over towards the right, and I'm going to head towards the speaker that's producing the sound. If I head towards the speaker in this car, then I measure the sound waves arriving at me in the car. As the driver of the car, I measure them arriving more rapidly. I measure their speed as larger. Larger by an amount of my speed traveling towards the speaker. And that probably seems obvious, or it seems natural, right? If the sound waves are traveling from left to right towards me and I run towards them, they're going to approach me faster. So I measure a higher speed. On the other hand, if I turn the car around, now I'm going to drive away from the speaker. If I drive away from the speaker, then, well, I'm driving towards the right. The sound waves are traveling towards the right. I'm going to measure the sound waves as approaching me less fast than the speed of sound. And that's because they're going to have to catch up with me. So I'm running away, they're going to have to catch up with me, and so I see them going as less fast. And so if you move towards the source of sound, you see the sound through the air, you see the sound waves traveling faster. If you move away from a source of sound, you see the sound waves traveling slower. And here's just a couple of examples. If I was moving towards the speaker at 40 meters per second, I'd see the sound waves traveling at 380 meters per second. That's what the driver would measure. If I was moving away from the speaker at 40 meters per second, then I'd see the sound waves traveling at just 300 meters per second because of my motion through the air. So that probably all seems kind of obvious facts about sound waves moving in air, and if you move in the air, you'll see a different speed for the sound waves as they move through the air. But supposing we weren't absolutely certain that sound travels in air. Supposing we weren't certain about that fact, then you could actually use the fact that if you drive towards the speaker, you see a higher speed. You drive away from the speaker, you see a reduced lower speed. You could use that observation of two speeds approaching the speaker, receding from the speaker, of 380 meters per second and 300 meters per second. You could use that fact to infer or support some ideas, some hypotheses. You could infer that, well, that's consistent with the existence of air, and that air, there's an air reference frame that the car is driving through. It would be consistent with your motion at 40, I put it miles per hour here, it's 40 meters per second, sorry. 40 meters per second through that reference frame to the left and right. And it would be consistent with the idea that sound is a wave in the air reference frame, and that if you move through that reference frame, you'll see a different speed. And so you could, if you weren't certain about the existence of air supporting a sound wave, you could infer the existence of air and the sound as a vibration in air based on the fact that you would observe different speeds of the sound waves as you moved towards the speaker and away from the speaker. So that would be evidence supporting the idea that air is a wave in sound, a vibration in sound with a certain speed. Well, that's exactly the situation we have with light. Now I've changed that slide, not the last slide, but the previous slide. I just modified it to not the case of sound and sound waves in air, but rather the case of light and light waves in ether. So if we went back to the 1800s, at that time we thought that light traveled at 3 times 10 to the 8 meters per second in ether, in a material called ether. So that was the idea. As a consequence of that, supposing we had a source of sound, that was the speaker, that we blasted over towards the right-hand side of the room. Supposing I had a source of light, and I blast that over to the right-hand side of the room. That's called a flashlight. So shine a flashlight over to the right-hand side of the room. If I was to drive towards the flashlight in my spaceship here, I would see a upshifted, I call it, a increased speed, because I'm approaching the light rays. They're heading towards me, I'm approaching towards them, which see a speed that is higher than the speed of light. If I was to drive away from the flashlight, the source of light, so here's my spaceship, I'm heading now towards the right of the room, the light's heading towards the right of the room, the light rays will be having to catch up with me as I travel towards the right of the room. I'd see a lower speed for the light rays. And so this is the same effect that we talked about for the sound waves, that if you approach the source of the sound waves, you see an upshifted speed. If you recede from the source of the sound waves, you see a downshifted speed. If you approach the source of light, you see an upshifted speed of light. If you recede from the source of light, you'll see a downshifted light. Now, we don't know that this is true or not true in the 1800s. This is just an idea. So the idea was that if we can measure the speed of a light ray. When we go at in different directions through the ether. So here's spaceship, I'm heading through the ether, heading towards the light, towards the left here. Here's a spaceship, I'm in the ether, I'm heading towards the right here. If we see a different speed for light as we travel through the ether, for example to the left and right through the ether, then that will be evidence for firstly evidence for the existence of the ether, for your motion through the ether on your spaceship, and for the evidence for the existence of the ether supporting the vibrations of light, that light were vibrations in the ether. So the basic idea was that we wanted to measure the speed of light as we move in different ways through the ether, and the signal of the ether and that light is a vibration in the ether should be that we see different speeds. See different speeds of light rays, and so we want to measure the speed of light rays. A sort of analogy to this is a kind of like the lifeguard analogies. So imagine you're a lifeguard and you want to prove the existence of the ocean and the ocean current, the movement of the ocean. So you could swim one direction through the ocean, and maybe you're swimming in the direction of the current. And you go relatively fast from the perspective of the land, say. You could swim the other direction in the ocean, so into the current. Now you're going to swim much slower from the perspective of the land. So when you move through the ocean, the lifeguard moves through the ocean. If it moves with the current, you get a fast speed. If you move against the current, you get a slow speed. Those two different speeds that the lifeguard swims at when they're moving with the current or against the current would be evidence of the existence of the ocean itself and of its current. We did the same thing with sound. When you move towards the sound source, away from the sound source, you do different speeds. It's evidence of the existence of sound being a vibration in the air that you're moving through. When you measure the idea is to measure the speed of the light. When you move towards the light source, away from the light source, if you see a different light speed, that would be evidence that you're moving through the ether, and light is a vibration in that ether. And so this is kind of an analogy to that, where the lifeguard proves the existence of the presence of the ocean and the current in the ocean based on their motion with respect to the ocean. We're going to prove the existence of the ether by our motion through the ether and measuring the speed of light. The problem with it, the problem in doing this is that, again, the speed of light is enormously large, 3 times 10 to the 8 meters per second, 186,000 miles per hour. So it's an enormous speed. And well, how fast can I, walk through the ether to just try and observe a different speed? I'm going to walk left and right through the room, but I'm going to walk left and right through, run left and right through the room at meters per second. So I'd only see a tiny, tiny, tiny change in the speed of light if I move through the ether with everyday velocities. So that makes the experiment very, very hard. You need very, very precise measurements of speed to make to test this idea, because you're only going to move at some tiny, tiny fraction of the speed of light through the ether. So that's the basic problem. And the interferometer, the Michelson interferometer, was the most precise device for trying to measure tiny, 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 tiny effects like that. So the idea in this picture here you see a cartoon, an interferometer. The light is shining in from the left-hand side, and we're measuring the interference pattern downstairs on the bottom. And now we imagine that this light, this coming in from the left-hand side, is a wave in the ether. So in this slide is filled up with ether. And this wave is vibrations in this ether. And the idea is to take the interferometer, look at the fringe pattern, and move it in the ether. move it through the ether. So I could push that interferometer towards the left-hand side. That would be like driving towards the loudspeaker, or it would be like the space rocket flying towards the flashlight. I should see a larger speed. I could also move the interferometer towards the right. Then the light ray has to catch up with the interferometer, and so I might see a lower speed of the light ray as it travels towards the right. Just like I could move I could drive away from the loudspeaker and see a lower speed. Drive away from fly away from the flashlight in the space rocket and see a lower speed. So I could move the idea of the experiment is to move the interferometer in the ether, which is supporting the light waves, and that will change the speed of light that you see in the interferometer. And that change of the speed of light means you will change the interference pattern. The interference pattern is between these crests and troughs that travel along the arms of the light ray. You'll change the time it takes the light to propagate along the lengths of the arms of the Michelson interferometer, so you'll change the interference pattern. So the basic idea is you measure the interference pattern with the interferometer sitting in the lab, say, and then you're going to move it over towards the right, and you look for a change in the interference pattern, which will correspond to a change in the speed of the light. Or you move it over towards the left, you look for a change in the interference pattern corresponding to a change in the speed of the light ray. It's a little bit complicated because you've got light going in all different directions here, so I don't want to explain all the details, but basically you're moving an instrument that is sensitive to the speed of the light ray. If the speed of the light ray changes when you move the instrument through the ether, you're going to see that effect in the fringe pattern that you observe in the interferometer. So this was the basic idea. It was a huge idea, and it was going to detect the presence of the ether. There's an equation that tells you the relationship between the fringe shift. So how many fringes the pattern will change by if you move the interferometer through the ether. And it's this equation here. And as I say, I'm not explaining this equation. It just comes about by tracking for each of these light rays, the ones that go left and right and up and down. You know, when you move the Michelson interferometer, how much do you change the speeds of the light rays, and therefore how does the fringe pattern change? And the end result is this equation here. This delta, Greek delta over here, this is the change in the fringe pattern. So it might say that, you know, you're going to get a fringe shift of 1 or 100 or 10,000, or maybe it's going to be really small because light is traveling really fast, and maybe so it's a fringe shift of 1,000th of a fringe, or a billionth of a fringe, or a millionth of a fringe. So this is the fringe shift, and then over on the right hand side is all the things that the fringe shift will depend on. There's a couple of things in black here that are associated with the Michelson experiment. The interferometer. You know, when you build an interferometer, you're going to use it with a certain color of light, wavelength of light. You're going to use a certain distance to your mirrors. L is the distance to the mirrors in this equation. So uppercase L is the distance to the mirrors. That might be, the scales are kind of meters for the distance to the mirrors. Lambda is, of course, the wavelength of the light. So, you know, that's going to be 400 nanometers if you've got blue light, or 700 nanometers if you've got red light. So that's the L and the lambda. They reflect the particular interferometer that you've happened to buy or use or make. V and C. V in green, C in red. These are the two speeds that are important in the experiment. So one speed that's obviously important is the speed of light. And we're exploring the effects of the speed of light. And so the speed of light is the C in this equation. The other speed is how you're moving through the ether. The V is the movement of your experiment through the ether. And so both of those matter. Actually, the comparison of those two, the relative size of those two, is really what matters. What matters is V over C, actually V over C squared. So this is the square of your speed through the ether divided by the square of the speed of light traveling through the ether. The problem is, you see, that this number here, v squared over c squared, that's going to be tiny. Imagine that you were using everyday velocities for v's. Those would be meters per second. So it would be meters per second over 3 times 10 to the 8 meters per second. That's an enormously small number. And worse than that, it's squared. It's 1 meters per second squared over 3 times 10 to the 8 meters per second squared. That's an incredibly small number. Although this is a big number here, the size of the experiment, L divided by the wavelength used in the experiment, that's a big number. It only partially compensates for the tininess of this number. So it's a hard experiment to do. The fringe shifts are going to be tiny, and you need big speeds. So how do they get large speeds? So they got speeds that were kilometers per second, tens of kilometers per second. How do they get speeds moving the interferometer of kilometers per second, tens of kilometers per second? Well, actually, we have speeds of kilometers per second and tens of kilometers per second. You see, the ether is filling the universe. It's what light exists in. Everywhere there's light, there's ether. We're riding a spaceship through the universe. This spaceship Earth, we're circling the sun, orbiting the sun, and that orbital motion is at high speeds. It's at about 30 kilometers a second. So we're on a spaceship that's running around the sun, and we're moving through the ether at 30,000 meters per second, 30 kilometers per second. Also, we're rotating. The Earth is rotating. The Earth is spinning a rotational motion on the surface of the Earth. Well, that's not as fast, but it's like scales of kilometers per second. And so we are actually ourselves moving on a spaceship fast through the ether. And so the idea was to use that motion. So part of the idea was that from 1 year to, from summer to winter or winter to summer, you change your direction through the ether by 30 kilometers per second, by a huge speed. That's because, in the winter you're, say, flying towards the right around the Earth. In the summer you're flying towards the left around the Earth, around the sun. When you rotate, when the Earth spins, again, over a day, between day and night, say, you're changing your direction of your motion through the ether. So we can use those things. So the idea was here's their experiment. This is the Michelson-Morley experiment. This is this big table with the mirrors and the splitter and a source of light and looking at the interference of the light. So basically, by having this sitting in the lab, they're flying it around flying it around the sun and spinning it around the center of the Earth. And so that's how they were going to detect the changes. As the Earth moves around the sun, there'll be a change on a yearly time scale. As the Earth spins on its axis, there'll be a daily change on that time scale too. And so that's what they used. I'll jump to here. They predicted that on a yearly basis, they'd see this fringe pattern change by about 1/10 of a fringe. So it's a small effect, but actually it's pretty easy to measure 1/10 of a fringe shift. They observed nothing. They observed no fringe shifts. What they effectively observed is that it seemed that the speed of light was always the same, no matter whether you traveled towards or away from a light source. No matter how you moved through the ether to the left or right, the speed of light was the same. So light was somehow fundamentally different from sound. So for sound waves, if you travel towards the source of sound waves through the air, you'll see the speed higher. If you travel away from the sound waves, you'll see the speed of sound lower. That's because the air supports the sound waves. The sound waves are vibrations in the air. But it seems that for light, if you move towards the light source, you always see the same speed. no matter what speed you head towards it. You move away, you see the same speed. No matter what speed you move away, the speed was always the same. There seemed to be no ether that supported the light waves, like there was sound, like there was air supporting the sound waves. So this was a big puzzle. We're going to talk about the resolution of this puzzle in the next class. The only way to fix up this puzzle is to fix up our notion of speed and space and time, the ingredients in space and time. So next class, next week, we'll start talking about relativity. I'll finish there. We talked about the interferometer. We talked about it for using routine things, measuring lengths, measuring wavelengths, less routine things, gravity waves, and detecting the ether.